we talked about on Friday that if you can base an unbiased estimator on a sufficient statistic, it turns out that that unbiased estimator is a minimum variance unbiased estimator. So it gives us another way to find minimum variance unbiased estimators. And then using sufficient statistics, which again are good ones to use because those sufficient statistics are the ones that basically you get all the possible information out of them that you can based on the sample. So anyway, let's talk about how we can find it in this particular one. So I started this off, and I want to go back and restart it anyway. That was why I erased it at the beginning here. So we're going to look at a gamma distribution. We want to show that we have a sufficient statistic for a particular parameter and then try to figure out an unbiased estimator for theta. So if we had a regular or just a general gamma distribution, we know that's x to the alpha minus 1 e to the minus x over theta over gamma of alpha theta to the alpha. Now it's asking us to find a sufficient statistic for 1 over theta and alpha equal to 1. There's nothing special here about alpha equal to 1, by the way, to be able to get a sufficient statistic. So to do that, to show that we have a sufficient statistic, let's do that writing it in exponential form again. We could either write it in exponential form or we could do the factorization theorem. In fact, let's do the factorization theorem part. That might be a little bit easier. So because I don't really want to write all of this in terms of an exponential function. So we remember the factorization theorem says that we have a function of x without the parameter and then a function that has the parameter in it and then some function of the x. Well, in this case, we can do that as, I can write this as, I'll just emphasize it this way. The 1 over gamma of alpha times x to the alpha minus 1. So this is the part that has no theta. And over here, we would have 1 over theta to the alpha e to the minus x over theta. So here is our part that has the theta with the x in it. So the function that we can use for the x here would be the sum of the x's. So from this, just from the factorization theorem part, we see that y equaling the sum of the, actually I didn't quite use the factorization theorem part right, but y equals the sum of the x sub I is sufficient for, in fact, it's sufficient for 1 over theta, regardless of what the alpha is here, because I could rewrite this part here as 1 over theta to the alpha, treating the 1 over theta as the parameter, and this would be x times 1 over theta here. So I'll circle those in red to show that I'm rewriting those. So I really do have the parameter as my other variable in this one. So I've got my function of x and my function of the parameter. Now the reason why I'm using the sum of the x sub i's here by the factorization theorem is because, remember, the factorization theorem says we really have this all multiplied together, and when we multiply these e to a power, we do the sum and the exponent. So I really do get that y is sufficient for 1 over theta based on this. But this is by the factorization theorem. Okay, so it asks us to show that it's sufficient, which we did. It also says that y has a gamma distribution with parameters n and 1 over a theta. Notice I didn't do anything special here with the gamma distribution. I just have the parameters here. I could write these as 1 over theta if I really, really wanted to. Flip some things around. And the alpha is equal to 1. So let's do that now to get the second part. So if alpha is equal to 1 and our theta is replaced with 1 over theta, then your PDF would look like, well, there wouldn't be an x anymore. Gamma of alpha is 1. So you would have e to the minus x theta, and then there would be a theta in front, because the 1 over if I replace the theta with 1 over theta, it would flip to the top. So this would be what your PDF would look like. In particular, this is exponential with a parameter 1 over theta. Y then is a sum of exponentials. So y is a sum of exponential distributions. And I should have been more specific. It's a sum of independent exponential distributions. So that implies that y is a gamma distribution. Each of the alphas is 1, and there's n of them. So we would have n times 1, or n, for the new quote-unquote alpha, and your theta doesn't change. So it would still have 1 over theta. So the showing that y is a gamma distribution is the fact that we're adding up a bunch of independent exponentials to get a gamma. All right. So then the last part asks us to show that n minus 1 over y is an unbiased estimator for theta. Okay. So to do that, the first thing we need to do is I need to figure out what the expected value of y is. All right, well, we know that the expected value of y for our purposes is going to be n over theta, because it's alpha times theta. So we need to find the expected value of 1 over y first to see if we can get that n minus 1 piece in there to find an unbiased estimator for theta. So let's look at the expected value of 1 over y. And we're going to use the fact that y is gamma in this case to do that. So if y is a gamma distribution, then I can do the expected value is going to be the integral from 0 to infinity. We're going to do a 1 over y times a y to the n minus 1, e to the minus x times theta over gamma of n, and then 1 over theta to the n. Yeah, and then dy. This should be a y here because I'm doing the distribution of y now. All right, so this, now if we do a little bit of algebra, this is y to the n minus 2, e to the minus y theta over, this is gamma of n, and this is 1 over theta to the n. And now I need to do some manipulation so that I can see what this integral is. Well, if I pull out a 1 over theta, I can make this an n minus 1. And I could also use our property of the gamma function to get this in terms of n minus 1. So let's do that. We have y to the n minus 2. We have y to the n minus 2. And we have an e to the minus y theta. This is n minus 1 gamma of n minus 1. And this is 1 over theta times 1 over theta to the n minus 1. So now, dy. Now I can pull out this n minus 1 and this 1 over theta. So I get theta over n minus 1, integral from 0 to infinity, y to the n minus, I'm going to write it as y to the n minus 1 minus 1, e to the minus y theta over gamma of n minus 1 times 1 over theta to the n minus 1. This is now a PDF. I'm integrating a PDF of a gamma distribution with n minus 1 for my alpha and 1 over theta for my theta. So this is going to equal 1. So I just get theta over n minus 1. So your expected value of 1 over y is theta over n minus 1. So I can use n minus 1 over y is my theta hat. And that's my unbiased estimator for theta. And since it's based on a sufficient statistic, this is a one-to-one function of a sufficient statistic. Y was sufficient. We get that this is a minimum variance unbiased estimator in this particular case. All right, let's see if we can do another one. So this particular problem asks us to show that a specific function is a minimum variance unbiased estimator. So let's use this idea again that we have a sufficient statistic. All right, so it wants to show that it's a minimum variance unbiased estimator of 1 over theta. All right, so the first thing we notice is that this particular PDF, if I write it as e to the natural log of theta and then plus a theta minus 1 natural log of x, do e to a log and then break up the log over the product and then bring the exponent down in front. I can also write this as e to the log theta minus log x plus theta minus 1 natural log of x. So this part here is my factorization part. Here's function of theta, no x's. Here's function of x, no thetas, multiplied together. So therefore, this is exponential form. So we get that y equals the sum of the log of the x sub i's is sufficient for, I might as well make it sufficient for theta or 1 over theta, either or. Because if I have sufficient information for theta, I have sufficient information for 1 over theta. I can do the reciprocal and get an estimate. All right, so let's see if we can do the expected value of y again. Expected value of y in this case would be what? Well, I would do the integral from 0 to 1, and I would do natural log, well, I would do n times this because I have n of them. I'd have natural log of x times theta x to the theta minus 1 dx. I have to do a little bit of integration by parts. If I do, my u is natural log of x and du is 1 over x. My dv would be theta x to the theta minus 1, and my v would be x to the theta. So we would have x to the theta log x evaluated from 0 to 1, and then minus the integral from 0 to 1 of x to the theta minus 1 dx. So I don't know why I wrote d theta over here. This should be dx. So this part here, when I plug in 1 for x, I get 0 for the natural log. If we put in 0 for x, this part's 0, this part's negative infinity. So technically you would have to use L'Hopital's rule, but if you use L'Hopital's rule for any theta here, arbitrary theta, as long as theta is positive, this will always turn out to be 0. So this is going to equal 0 no matter what, regardless. This is, we can do this antiderivative pretty easily. This is going to be minus 1 over theta x to the theta evaluated from 0 to 1. So we get, in this case, negative n over theta for the expected value of y. The problem asks us to show that negative 1 over n, sum of the log of x's, is an unbiased estimator for 1 over theta. So we have, right now, I've got expected value of the sum of the log of the x sub i's, that was my y, is equal to negative n over theta. Well, I want an unbiased estimator for 1 over theta, so I would move the negative 1 over n out in front. I didn't mean to put that in there. Oh, shoot. I can't erase things, apparently. For today, I don't know what the technology problems all over the place today. This will be my theta hat. This is an MVUE for 1 over theta. And again, the reason why it's a minimum variance unbiased estimator is because this is a sufficient statistic for 1 over theta. Because it was sufficient for theta, it's sufficient for 1 over theta. Anytime you have a statistic that is sufficient for a parameter, it'll be sufficient for a one-to-one function of the parameter as well. Because if I know, think about it the other way around, if I know what the one-to-one the output is for a one-to-one function, I know what the input had to be. So if it's sufficient for theta, it's sufficient for 1 over theta. And then since we're basing the statistic on we're basing our estimator on a sufficient statistic, it has to be a minimum variance unbiased estimator. Okay, so that's the idea behind that. So let's switch gears a little bit, maybe, if I can get the page to flip, and talk about Neiman-Pearson lemma that was in the video that I asked you to watch for today. I know it seemed a little bit weird, but the idea behind the Neiman-Pearson lemma is the fact that you're trying to find a critical region that creates the greatest power. So again, for critical, we always choose the critical region based on the significance level. And if we can pick a critical region that has the best chances of rejecting when we're supposed to, then that's our best critical region. And the Neiman-Pearson lemma gives us a way to figure out how to get at that best critical region. So let's see if we can do this by a few examples, several examples in fact. So let's say we have two density functions. So this is a little bit different than what it was talking about in the video, but it's the same kind of concept. We're going to do the same kind of thing. So we're going to have a random variable that we're going to test whether or not its density function is the first one or the second one. Now, instead of doing a big, large random sample, we're going to do one sample, literally a sample. Not several different samples, not several things in the sample, just literally a single observation. And we're going to see whether or not we can come up with an idea that tells us what the best critical region is for this particular hypothesis test. So again, the idea was that you would do the likelihood, now in the video it was the likelihood of theta naught over the likelihood of theta 1. So that was the parameter. In this case, we're trying to figure out the likelihood of which distribution are we using, but it's the same concept because we're still going to do PDF divided by PDF. All right, so the null hypothesis in this case is the fact that we're using this PDF, the 2x. So and it's a single observation, so we don't have any products going on here. So the single observation would be then that likelihood would be I would plug the x value into the first PDF and get 2x. Or if it was the alternative hypothesis is true, I would have 1 here. Okay, so that would be our likelihood ratio for this particular hypothesis test. We need this less than or equal to some positive constant. That's what the Neiman-Pearson lemma says, is that we have to show that this is less than or equal to some positive constant to get at it. Okay? So, in this case, we would need that our 2x is less than or equal to k, or x is less than or equal to k over 2. That's the c in this case. That's our c. We never ever figure out what the k is. We just want the positive constant k and then see if we can determine what the c is from the given information. And if we can, then we know that the k will exist. Because if we can figure out the c, then we know the k. The whole idea with this k part is basically telling us what the form of the critical region needs to be. Then we have to go hunt the c. All right, so remember that this refers to your critical region. Your critical region is a probability that you reject when you're not supposed to. So we want the probability that our x lies in our critical region given the null hypothesis is true to be 0.1. This is how we're going to find the c, right? We want the probability that the null hypothesis, that we're in the critical region given the null hypothesis is true. So this is the probability that we reject when we're not supposed to. It's that type 1 error. We want that probability to be 0.1. Well, if the null hypothesis is true, this is the distribution we have. So we want this probability that x is less than c for that distribution to be 0.1. So we want the integral from 0 to c less than c, right? And x is between 0 and 1, so we want the integral from 0 to c of 2x dx to equal 0.1. So we get x squared evaluated from 0 to c to be equal to 0.1. So c squared equals 0.1, or c is equal to square root of 0.1. So our critical region C, which would be the set of all x such that x is between 0 and square root of 0.1. I know my x is not going to be less than 0 because of the supports that were given, right? So I want this to be, this is my critical region. This is a best critical region in this case for this hypothesis test. Okay, so again, the process was we created the likelihood ratio. In this case, the likelihood ratio was much simpler because we had a single observation. We set the likelihood ratio to be less than or equal to some constant, and then figure out what the form has to be in terms of the x's, whatever that happens to be. And then we find the c by computing the probability of making a type 1 error, whatever that happens to be. Okay. So this one hopefully was a little bit more straightforward than the one we did in the video, but let's see if we can do ones that are a little bit more complicated. All right, so let's say we have, this is out of your book. We've got a random sample that comes from a normal distribution. You know the mean, but you don't know the variance. And this one asks us to create a best critical region and show that as of a certain form. So since I don't have the n given to us in this case, I really do need to create that likelihood ratio. With a product. So our theta naught here, of course, this is our 4 in this case, because theta naught's referring to the value of the parameter for the null hypothesis. Our theta 1 is 16 because that is the value of the parameter for our alternative hypothesis. All right, so the likelihood function again is the product of your PDFs with the sample plugged in. I'm going to write the index here one time and one time only, and usually I will eliminate the index, but just to illustrate what's going on. So we have a mean of 0 and a variance of sigma squared, but in the first case I want the sigma squared to be 4. So this will be 1 over 2 square root of 2 pi, and then e to the minus x squared over 8. Remember that the form of the normal distribution is 1 over square root of 2 pi sigma squared. So I just did the square root of the sigma squared. And this is e to the minus x minus mu quantity squared over 2 sigma squared. So that's where the 8's coming from. You'll have a similar form in the denominator, except that in this case our sigma squared is 16. So instead of a 2 out in front, we'll have a 4. And instead of an 8 in the denominator, we'll have a 32. All right, so When we do this then, we want to simplify this. Well, notice when we simplify, the 2 pi's will cancel, and the 2 and the 4 will cancel, and you'll end up with a 2 on top. But we're multiplying that 2 by itself n times. So we're going to get a 2 to the n out in front, without any doubt. Okay? And again, that's coming from the fact that this 4 is going to flip up into the top, so you'll get 4 over 2, which will give you a 2, and it's multiplied together by itself n times. The square root of 2 pi's will cancel again, and now I need to subtract these exponents, so you'll get an e to the negative, if I factor that out. I've got a sum. I've got a sum of, we'll have x squared over 8 minus x squared over 32. So you get 3x squared over 32 there when we subtract. We want this less than or equal to a k. Well, we're almost home now, because all I need to do is, notice this is the form that I'm trying to get to. This sum of the x squareds is greater than or equal to some constant. The c is just representing some constant. So I need to divide by the 2 to the n. Should have an x of I technically there, squared. Now do your log of both sides. And I can pull out the 3 over 32 in front of the sum. So I took the log of the right-hand side and just rewrote it as a difference. Multiply both sides by 32 over 3. It'll flip your inequality. It's negative, sorry. Natural log of k minus natural log of 2 to the n. This is your c. So that took care of part A, showing exactly what it asked for, showing that your sum of your x of i's squared has to be greater than or equal to the constant, some constant. So that's part A. So this is our best critical region. So part B now asks us to figure out the value of c given that alpha is 0.05. So again, this is our critical region. We now want the probability that the sum of the x of i's squared is less than or excuse me, is greater than or equal to some constant, given that the variance is 4. We want this equal to the 0.05. This is our alpha. So again, the probability that a sample lands in the critical region, given the null hypothesis is true. There's a lot of words in this short little statement, right? Given our sample gives us a statistic that's in the critical region, provided the null hypothesis is actually true, is small. That's our significance level, right? So again, this expression is probability of making a type 1 error. It's the whole idea here. Okay, so what did this problem say? Well, this problem wants us to figure out this probability. Well, we remember that each of our x's is a normal distribution. And if we square normals, we think chi-squared. But remember, we have to standardize that thing. So the probability that sigma squared times the sum of x of I over sigma squared is greater than or equal to c, given that sigma squared is 4, is 0.05. So now I know that this piece, this is chi-squared of n. Well, if I'm given a couple of things, I think they tell us that the n is 15, and I know that I want the null hypothesis to be true. So now we want, for a chi-squared random variable, we want the probability that 4 times the sum of x sub I over 2 squared is greater than or equal to be some constant is 0.05. But this is some chi-squared random variable, I'll say y. This is chi-squared of 15 now, because it says we had 15 degrees of freedom. I know that that is a chi-squared of 15. So if I divide by the 4, then I get my c over 4. So what does the c over 4 have to equal to? Well, you go look up your chi-squared at 0.95. I think that's the way they write it in the book. If I remember correctly, nope, that's not right. This is 0.05. They write it that way because they want it as a right-tailed probability. This is 0.05, maybe, of 15. So you can do this in Excel using your chi-square inverse right tail, or you can do it by looking it up in your book, assuming I can get to the right page, since I don't really feel like flipping over to Excel. At 0.05 for 15 degrees of freedom, it's 25. So it's 25.00. So the C must be 100 in this case. Okay, so the idea here is that to get our critical region, to make sure our probability of making a type 1 error is equal to 0.05, we need to make sure that our C value, our sum of our x squareds, is equal to 100 or more, to make sure that our, well, when we set it equal to 100 is our critical value, then we know that we'll have a probability of 0.05 of making a type 1 error. All right, so the last part is probability of making a type 2 error. That's what the beta is. And the probability that you're not in the critical region, given that the alternative hypothesis is true. So this is the probability that you're not in the critical region, do not reject, given that you should. So this is our beta. This is talking about the power idea. So same idea here, probability that your sum of your x of I squared is less than 100 in this case. We just found the 100. Given that sigma squared is 16. Okay, so this will be 16 sum of x of I over 4 squared is less than 100. Because again, the alternative hypothesis is true here. So instead of having a 4 in front, we're going to have a 16. That's what we want to calculate here. So we need the probability that our sum of the x of I squared over 4 is less than 100 over 16. And this now again is a gamma, or excuse me, not a gamma. This is a chi-squared of 15. So 100 over 16 is what? Let's see, that's 25 over 4. Right, so that would be 6.25. If I go to the gamma distribution, you can do that on your, by the way, you could do this on your in Excel. It'll give you a much better approximation. I just don't feel like jumping over to Excel on here. I've had enough technology issues today. I'm going to stay on the screen. This is 6.25, right? It's 25 over 4. If you go to your gamma I keep saying gamma, chi-squared distribution on 15 degrees of freedom and look up 6.25 in the table, you'll see that there's a number that's close to 6.262. So this is approximately 0.025. That's what that probability corresponds to. So this is your beta. Your beta is approximately 0.025. So this would tell us that our power, which the book likes to use as a K, the power based on a variance of 16, that's what these of 16 idea would be, this is going to be equal to 1 minus that probability, or 0.975. So pretty powerful test in that case. But that's the idea of how you can find these alphas and betas. If I can get this to select. There we go. See how much time. Okay. So let's do another one. I think I'll do one more, and then we'll do more of these later. How did I do? I just switched pages. Apparently. I'm not sure how I even switched pages, but it switched pages on me. That was very weird. Okay, let's do this 10.3-3. Same idea. In this case, we have an exponential distribution, and we want to show that a best critical region can be based on the sum of the x of i's. Okay, so let's do the likelihood of theta naught over the likelihood of theta 1. This is Neiman-Pearson lemma again. This one says I want my theta naught to be 3, because again that's coming from the null hypothesis. This one we want it to be 5, because that's coming from the alternative hypothesis. So for this one then, when we do this, we want to do the product of, this is exponential, 1 over 3 e to the minus x sub I over 3. On top, on bottom we get 1 over 5 e to the minus x sub I over 5. All right, so we want this less than or equal to a k. Now I didn't mention this earlier in the video, but I did mention on the video that I asked you to watch for today. The whole idea that we want this likelihood ratio to be small whenever we're in the critical region is that if we're in the critical region, we would like the likelihood of the likelihood that the alternative hypothesis is true to be larger than the likelihood that the null hypothesis is true. We don't want to reject, right? So this likelihood ratio that we're doing corresponds to the fact that we are looking for a sample where the likelihood that you're in the critical region is small if you really should be rejecting. Okay? So we don't want it to be, the likelihood that the parameter is the null hypothesis parameter is small if we're in the rejection region. That means we should reject in that case. That's the idea of making this ratio less than or equal to some constant. All right, so now we get to play the algebra game. This is 3 to the n. This is going to be a 5 to the n when you reciprocate. So you're going to have a 5/3 to the n. Again, we'll subtract exponents here, factor out a negative. We need to take a 1/3 minus a 1/5. So that's 5/15 minus 3/15. We get 2/15 x sub I, less than or equal to k. Okay, now mainly we're just trying to get to where we have a statistic. The sum of the x sub i's in this case is what it's asking us to do. What do I have to do to, and again, all I care about is that there is a constant on the right-hand side. Not x's, a constant on the right-hand side. How do I get to that point? I need to move this over, either by multiplication or division. I'm going to need to take a log. Neither of those is going to change this sign. However, the last thing I'm going to have to do is move that negative 2/15 to the other side. That will flip the sign. So by the time I get there, I'm going to get the sum of the x sub i's is going to be greater than or equal to some constant. So this is the form of our critical region. Okay. Again, let me just explain in words how I got to the C. Because again, we don't care what the mess is. We just want the mess to be a constant. We'll figure out the constant later based on the probabilities that we're going to compute. So again, how did I get to this point? I need to move this constant to the other side. Does not flip the inequality. I need to take the natural log to get rid of the e. Does not flip the inequality. I need to factor out the 2/15 and move it to the other side. That will flip the inequality at that point. So that's why I've got sum of the x sub i's is greater than or equal to some constant. Okay. Hopefully that makes sense. All right, so let's talk about then how do we find this value. So this was part A. Part B asks us to find the actual value of C, find the best critical region. So we want that the probability that the sum of the x sub i's is greater than or equal to C given that what is true? Theta equals 3 is equal to 0.1 in this case. Just changed it up on me. Okay, so they say use the fact that we know that if we put a 2 over theta out in front, I get a chi-squared of 24. Well, why is that in this case? Why do I get a chi-squared of 24 if I put a 2 over theta out in front? Let's think about this for a second. It's chi-squared of 24. I just want to show you how we can get at that derivation. So if we think about the distribution, let's call this whole thing y. If we look at the distribution function of y, this will be the probability that capital Y is less than or equal to little y. Our capital Y is 2 over theta. Let's just refer to this as x because the sum of the whole thing is the gamma distribution. Oops, I want this less than or equal to a little y. Let's solve it for y. This is now our cumulative distribution function. Cumulative distribution function of the x random variable, but with theta over 2y plugged in for x. So our PDF for capital Y will be the distribution function derivative evaluated at theta over 2y times the theta over 2 by the chain rule. Now again, remember this is gamma. Its PDF is x to the 12 minus 1 e to the minus x over 3, gamma of 12, 3 to the 12th. So theta is equal to 3 in this case. That's where I got the 3's from. So if I do this now, this is your PDF with theta over 2 plugged in for y. So we'll have theta over 2y plugged in for x, I mean. So we'll have 3 over 2y to the 12 minus 1, e to the minus 3 over 2y all over 3, gamma of 12, 3 to the 12th. So notice this is, write it this way, I'll have a 3 to the 12 minus 1, y to the 12 minus 1. This is now e to the minus y over 2. This is gamma of 12, and this is over, sorry, I don't want to write that down. This is 3 to the 12th, and then a 2 to the 12 minus 1. And I still have an extra that I forgot to write up here, 3 halves, because it says it's times 3 halves. All right, so far now we've got a y to the, and I'm going to flip some things around. This is 24 over 2 minus 1. This is e to the minus y over 2. That's good for chi-squared. This is gamma of 12 over 2. What do I want left? Well, for chi-squared, I need a, what? 2 to the r over 2 left, which I have here. Because I have 24 over 2 now when I put the 2's together and the 3's all cancel. So this really is chi-squared of 24. All right, so that was a lot of work to get at that you probably really didn't care about since they told you in the problem that it really was chi-squared of 24. But I wanted to show you where the chi-squared of the 24 came from. I thought it was a good review of stuff that we talked about last semester of how we got to that point. So anyway, the whole point of this is now, let's go back to what I was doing. This is what we want. If we multiply this by 2/3, this part here is chi-squared of 24. So if we go to the distribution table again and look up the C or sorry, I should write 3/2 C. No, I really shouldn't write 3/2 C. I should write C. Sorry. It's not been a good day. So this C needs to be chi squared of 0.1. So 0.1 of 24, which will be, according to our table, 33.2. And again, you could use Excel on that. So we want the sum of the x, 2/3 of the sum of the x of i's to be greater than or equal to 33.2. So our sum of x of i's will be greater than or equal to, that's going to be 16.6. When we divide by 2 and multiply it by 3, we would get, what, 49.8? So our critical region then will be the sum of the x of i's is greater than or equal to 49.8. I should probably really write that in terms of a ordered pair of things, since our ordered tuple of things, since our critical region is talking about samples. But anyway, that was kind of messy, but that was the idea. Notice that nothing different is going to happen here for part C. Right? The only place that theta equals 7 comes in is right here. This is where we would change our, well, and right here, I suppose. But the only difference that theta being 7 would make is that I would have a theta in that where that 5 is, excuse me, I would have a 7 where that 5 is. Notice that we don't even pay attention to that here for the form of the critical region, right? We just say that it's greater than or equal to some constant. And then come over here and figure out our critical region in terms of that some constant, but we're using the null hypothesis in this case. So it doesn't matter. So D says, is the common region for parts B and C a uniformly most powerful critical region? Well, yeah, it is in this case. For a hypothesis test for theta greater than 3, it absolutely is a uniformly most powerful critical region, one that works no matter what the theta is, as long as the theta is greater than 3, because the theta doesn't matter when we're doing this computation. We get the same exact critical region no matter what the theta is, as long as the sample size is 12. If the sample size changes, then we'll get a different critical region. But if that sample size changes, it stays at 12, the C will not change because the theta has no bearing on it at all. So that's why that ends up being a uniformly most powerful critical region in this case. All right, we'll do some more of these on Wednesday, hopefully live, but perhaps not, because goodness only knows if my internet will work or not. So we'll talk to you then.